speaker for this presentation. Russell Green, current Director of Product Applications at Automata, and previously the Head of Partnerships and Senior Product Manager at Synthase, and Senior Manager Field Projects at Beckman Coulter Life Sciences, has been at the forefront of developing lab solutions that optimize workflows, enhance data accuracy, and accelerate scientific discovery. Russell's expertise lies in harnessing automation to reshape research processes, enabling scientists to achieve greater efficiency, reproducibility, and scalability in their experiments. Russell, thanks for joining us today.
Hi everyone. Thank you very much. Thanks for the great introduction and thanks for joining. So I wanted to speak today in a bit more detail about some of the larger automation projects that we've done and how we are working towards bringing together automation technology to go maybe a little bit beyond what current people consider to be automation and take that into a world where we can really start thinking about what the lab of the future might look like. I'm going to cover a few different topics today, but in particular, I'm going to talk about the larger systems, but I'm going to show you how you might also consider starting that journey towards automation as well. So don't be too concerned if you see some scale of automation that perhaps is a little bit beyond what you tend to think of on an everyday basis. So I'd like to start off with a quote, and this is a real simple one from a paper back published in 2018. It says, "The automation of science bears the promise of making better decisions faster." And I think that for me speaks to why we might automate in its most simplest terms. And I've given a fair number of talks about adoption of automation and how we might drive more to automation in our industry. And it always comes back to these reasons to automate and what's going to be your driver. And at the core of everything is this idea that automation should bring us more data of higher quality faster. That's what it's all about. And it means that race towards getting more data and higher quality is very real. And there are some labs out there that are really pushing the boundaries on what you can start doing with current automation. And I think this is all about better data integrity, more data and greater data points around a single particular experiment and more of them. So with that, I don't need to think that this should be onerous either. I mean, this change should not feel painful. It shouldn't really be that disruptive. And actually, in the longer term, it shouldn't be expensive. Quite the opposite. I think it should actually drive costs down, even though there might be some initial outlay. But one thing I want to get through in this talk today is that we should be planning our journey to infrastructure level automation now. And I'll speak about what I mean about infrastructure level automation in a moment. So as much as anything, adoption of automation is a change management problem. It's that idea of, well, we need to identify something that's going to be worthwhile automating and then start thinking about what our plan to do that is, and then think about what the plan afterwards is. And a lot of what I'm going to talk about today is the longer term view. When we're thinking about the automated systems, and in particular, this is our view of things, we should really be thinking about how we best utilize what is existing. So first of all, space. Space is actually a real problem for an awful lot of laboratories right now, especially when you look at southern areas of the UK where I'm based, or East Coast US, where the cost of lab space per square foot or square meter is extraordinary at the moment. And so how do we maximize that space and get the most out of it? We need to think about the instruments as well. And we probably have an awful lot of instruments in place, and an awful lot of them are probably actually more automation friendly than we realize. And so how do we utilize those instruments to maximize their capacity and get the most out of them? And last but certainly not least, how do we utilize our existing people? So another one of the big drivers for automation is to really free up some very talented people and very skilled people to do what they do best, rather than focus on doing things which perhaps are not best use of their skill sets. And so automation is often about how do we do more with what we've got, and maximize and free up those people to really focus on the interesting things like complex experimental design or gaining insight from all the data that has been gathered. And if we use all of the things, we're really looking to achieve some things like long-term savings. I mean, this isn't always about money, but let's face it, there should be realistically a financial return on investment in automation. We need to figure out what that is and how we generate those savings. I have an example or two later on in this talk. As I said, it's really all about data when push comes to shove. And so it's about achieving this unified, robust data set. So deep data, well characterized with metadata and stored in a unified format that we can reuse again and again and again. And of course, modular adaptable systems. And this has actually been a big pitfall of automation over the past 2 to 3 decades as it's been gaining traction in life sciences, that automation is often developed to run a single thing. And we always talk in automation projects about, but we want to have flexibility, but you do realistically have to rein a project into thinking about that first achievable workflow. But of course, if we can really implement automation in a modular, adaptable way, then we're future-proofing ourselves. And so we need to think about, well, what can this system do later as well as what can it do now? What do things look like today? Well, in most labs, we see a lot of manual experimentation in quite tight spaces. So speak to that space problem again. But it's not just manual either. I don't want to ignore the fact that there are an awful lot of people that have implemented automation in life sciences already. But what I would tend to look at right now when I see automation in our workplace, and I've been working in this industry for a while, is sometimes a little bit beyond this, but an awful lot of it is what I would call appliance-led automation, which is serviced by humans. And that could be something, so what I mean by appliances, it could be something from a plate washer to an automated liquid handler to a plate reader, maybe some form of digital data capture, but often that is bridged by someone writing things down in a lab book before delivering on a Friday afternoon their final entries into their ELN. And I liken this a little bit to a kitchen. I'm a fond baker, and I look at all of the appliances around me, and they're all little bits of automation. So my dishwasher, my cake mixer, my oven, even, they're all different forms of automation in some sense that are doing tasks for me that I don't have to handle manually. But I spend an awful lot of time in between all of those things, bridging the gap. And so my baking process uses a lot of appliances, but is not automated from an end-to-end perspective. And this is true in this lab state as well, where these are all fantastic devices in their own right, but we need to have someone sat in between those, and all of a sudden that person becomes a break in the chain of custody of operations, or can't be there all of the working hours that we could possibly run all of those devices, or many other problems presented by a human being in the middle. So we want to try and get away from that and go to something more. If you add on to that, there's an awful lot of talk about how areas of life sciences needs to move towards adopting Industry 4.0 principles. And when you look in this in the context of digitalization in science in particular, there are kind of 3 core elements you can pick out that come up time and time again. One of them is connect everything. So this is not just about Internet of Things. It's about making sure that everything works together. You're gathering all the data and everything and bringing it together into one place. 2, establish automated end-to-end workflows. And obviously this is an area that's particularly leans itself to the content of this talk today. And then 3, implement advanced analytics. So gain insight from what comes out of steps 1 and 2 and utilize that to make better decisions about what goes back into steps 1 and 2. I'm going to speak to some degree today about those first 2 points. So how do we address connecting everything both physically and digitally, and about how do we establish true end-to-end workflow automation. My company, Automata, doesn't really get into advanced analytics, but certainly everything we do enables that to happen in a more efficient way. I also want to talk a little bit about what a journey towards infrastructure level automation would look like. And again, I'll do a bit more definition of our perception of that infrastructure level automation in a moment, but the way, in its simplest form, the way this transition looks, and we see this happen in some organizations already, is you start off with your manual processes or even your appliance-led processes. So maybe even at the extreme end of that, a fairly complex liquid handler. And you might move that into small islands of automation. So I might take a small cluster of devices and join them together with a robotic arm so I can service a subset of my workflow, my overall experiment. If you're then thinking about joining a group of those together, you might then start getting towards whole workflow automation. So rather than just having small islands that service a particular part of the experiment, I'm now thinking about putting something in one end and getting endpoint data out of the other. And then if you go beyond that, you start thinking about whole or whole facility or even multi-facility automation, where you're looking about how does an experimental campaign run through a whole series of different labs that are all running interconnected automation. And again, I'm really going to focus on the last two of these today. I will speak about small islands of automation. It's very much part of our core business, but really as a stepping stone towards how we think about automating entire processes or entire facilities or entire experimental campaigns. So what shape can whole workflow or whole facility automation take? And we cluster these into four different types when we think about them, and they all present different challenges and different benefits when you solve them. So there's one called end-to-end automated workflows, which I've touched on already, where you take a series of subset components of automation that maybe deliver on individual steps of a workflow, and you bring them together into something more holistic. And we've got examples of these as I go through them in a bit more depth in a moment. We also have what I would describe as multifunctional centralized work cells. So this is now one work cell that can serve many purposes. So almost like a core facility for a building that can run many different functions on demand. We then have multi-site decentralized automation. So rather than being something which is centralized and all in one place, now we're talking about automation that perhaps spans across several distinctly separated by geography laboratories, where we perhaps want to run the same kind of thing in all of those different spaces, but maximize the utilization of all of those. And this sort of scenario applies in particular to larger global organizations where you might have many sites servicing clients, but all for the same kind of activity. And then last but certainly not least is multi-work cell facility infrastructure automation. So now I have automation running throughout my building or throughout my facility or my site, but it's joined together. And so the way that I'm actually running all of that is really thought about as one large set of systems rather than a number of individual work cells that I have to think about individually. So diving first into the end-to-end automated workflows, I'm going to utilize a case study that we've worked on for something called NIPT. I'm not going to go deep into the science of this today, but NIPT stands for non-invasive prenatal testing. This is a clinical genomics workflow. Non-invasive prenatal testing is a method whereby you can take a blood sample from a mother, so maternal blood, and diagnose potential conditions of the fetus quite early on in that process by actually taking some of the fetal DNA out of that maternal blood. Very commonly used to look for things like trisomy early on in a pregnancy. The general workflow for this is that we need to take that plasma or take that blood sample and isolate the plasma. And then from that plasma, isolate what's called cfDNA, so circulating DNA. So this is now, I should say circulating fetal DNA. This is now bits of DNA that have passed through the placental membrane. They're in the maternal blood, and you can actually extract them from and separate those from the mother. So you're distinctly extracting fetal DNA rather than that of the parent. That DNA has to then be extracted, quality controlled, and then normalized before going into sample preparation for sequencing. So sequencing library preparation, which again has to be quality controlled, and then pulled ready for loading into the sequencer. So these are the steps that I'm interested in here from an automation perspective. This is pretty much an entire end-to-end workflow we don't tend to consider loading of sequences in this scenario part of that, because they themselves run for a long period of time, and it wouldn't be efficient to link them into an automated workflow. There's some real challenges around this. Like right now, people doing this who are using low levels of automation, there are an awful lot of manual touch points here. And that means that it becomes really hard to scale with the combination of existing people and devices that you've got. And so what we want to see is a route to scaling and increasing throughput. This is an incredibly popular technique for diagnostics these days, but we don't really want to increase the cost per test. Ideally, we want to see that go down so we can open this up to more people and more possibilities for that kind of testing. So if we now start looking at this in terms of current state, what we'll see is a lot of people running a lot of individual devices. So I can see here that for plasmid isolation, I'm using things like a liquid handler and a centrifuge to go through that process, perhaps some form of plate reader-based quantitation at this stage as well. I've then got people interacting in the middle here with nucleic acid extraction devices and more liquid handling, and perhaps returning to that plate reader for more data gathering. And then I've got more human interaction for these last three steps of library prep and library quality control and pooling, where I might be interacting with more liquid handlers, more kinds of analytical devices such as qPCR instruments and fragment analyzers and plate readers and whatnot. And the point being here is there's an awful lot of people, often overlapping. We have samples moving through all these independent devices, and they're very easy to mix up. So we have a really poor chain of custody, and we are not necessarily using all of these devices they're most efficient. This is a scenario that's very hard to scale. And even though we've implemented some liquid handlers here, this is still quite a complex scenario for running that entire workflow. The next step in this journey about end-to-end workflows is to start thinking about, well, where are the work cells I could build that really start maximizing an automation? And you start seeing just some discrete pockets here that are well worthwhile or starting out with automation. So we have our plasma isolation phase over here. Then in the middle, we have our circulating DNA extraction system combined with some normalization. And then we have a final system here that handles the last three steps of library prep, library QC, and pooling. And these are, to give you a sense of scale, I'll talk about our hardware a little bit earlier on. This system's around about 3 meters long, so about 9 foot, and depending on which part of the world you're living in and how you want to measure that. So we're talking about, in my world, reasonably small scale automation here. Like these are nice discrete work cells, and which one of these we might start with is probably defined by where our bottlenecks actually lie in our lab right now. But this isn't end-to-end automation. End-to-end automation is the scenario where I want to put something in at this end of the process, at the plasma isolation phase, and get my pooled library out the other end. And so then we start needing to bring together those workflows into something singular. And now we have one work cell that's significantly larger, but it isn't the same size as actually putting all three of those work cells together, because now we're able to look at where in our process, perhaps we had an underutilized device. Often the ancillary devices such as centrifuges or plate peelers or maybe even a liquid handler might be underutilized in each of those individual work cells. So when I bring them together, I can think, well, maybe I only need one of those rather than three, and I can bring that together into one workflow. But now, compared to the starting point for this, a single operator is able to present the system with all of the samples required for several batches of iteration of this particular end-to-end workflow. And at the end of that process, in the fridge at the end, receive pooled libraries ready for loading onto that sequencer. So this is an enormous step change in terms of automation from what they currently have. And there's some real upsides to this. So we see this single touch point for sample entry. We address all of those chain of custody issues about data. So we have, because we're using automation all the way through the process, we know where every sample is and what's happened to it at any moment in time, and we're tracking all of that data. And of course, the knock-on effect of this is some hugely dramatic throughput improvements And there are actually some other values that come out of this that I'll speak to you later on in relation to a slightly different project. So that's end-to-end automated workflows. Now, moving on to the next example, I want to talk about this. I've got to come up with a catchier phrase for this, but multifunctional centralized automation. And as I said before, what this is designed to do is servicing varying demands from all over a site. So let's say right now, my current state is I have many laboratories doing many different assays in a very, very efficient way. You may perhaps using some very underutilized small work cells. So I've got, I don't know, my genomics work cell in one lab, which is being used at 20%. I've got a cell-based assay work cell in another lab, which is perhaps being used at 25%, because there just isn't the demand from each individual lab. And then I've got other labs which are doing absolutely nothing. They have no automation. Everything's being done manually, and the people in that lab are running at 150% capacity. So this is a pretty common scenario, believe it or not, through when you look at a whole building and what everyone's actually doing. So now we look at a system like this, where we perhaps have a lot of different individual work units that have been brought together. So I've got, this isn't strictly true, but in here I've got a group of devices that is highlighted in yellow that is able to carry out some PCR-based analyses. I've got a group of devices in blue that can carry out some immunoassay capabilities. And then I've got a group in pink here which are able to carry out some cell biology activities. And they've all been brought together into one system. Now, this system could be used in many different ways and by many different users. So it's serviced by one host, one laboratory, a core facility, if you will, who is then able to, on demand, pivot the activities it's running and maybe even run some in parallel, depending on what the demand is coming from all over the facility. So here we might see a subset of devices being used for standard tissue culture operations, such as media exchange or passaging. We have a cell counter, we have an imager, we have a liquid handler, and an ink combined with an incubator and a media fridge are able to carry out most of those routine applications for standard tissue culture, mammalian tissue culture this is. We might then look at a subset of devices for running an immunoassay, such as an ELISA. Actually, this is able to run several different assays, this group of devices, because you can see here we've got a flow cytometer, a specific immunoassay system, and a plate reader. So this is a group of ancillary devices such as sealers and peelers and incubators combined with a liquid handler and a plate washer that can service several different endpoint analyses. But you can also see, if we look at this compared to the previous system, that we're now sharing resources between them. So the centrifuge, which is fundamental to both processes, is utilized by both of those. And we only need one of those to service a much higher capacity of assay space. And then as another example, we can just take another subset, so the sealer and the peeler and the sealer and the incubator and a different analyzer, along with the liquid handler and centrifuge, to carry out some qPCR assays for genotyping. Right, so now we're running 3 completely different experiments using just one platform, and potentially, depending on the implications for time constraints and things like that, we could run all of this using simultaneously. Alternatively, we could use the entire system for running one larger, more complex experiment, perhaps for end-to-end cell characterization in this case. So we're growing cells, maintaining them at different periods of time. We're carrying out flow cytometry-based analyses or imaging, perhaps counting cells, or even taking samples and putting that through into an immunoassay. So we can vary the way the system's using depending on the demand. And of course, the knock-on effect of that is our system uptime is dramatically increased. So rather than having several systems running at 20%, we now probably have one system running at more like 80 or 90% because we're servicing demand in a much more efficient way. We can also share some of these lower usage ancillary devices, so we need fewer of them, which obviously brings down the hardware and maintenance cost of the overall building. We can also then service this system by a single laboratory, so one set of experts servicing this for many, many users, which makes the whole support system much, much simpler as well. So the 2 examples I've gone through so far are kind of they're natural extensions to what people see right now in terms of work cell automation, something perhaps a little bit more complex. The next two examples of infrastructure level automation I want to speak to are a little bit more complex. So the first one I want to speak to is what I would describe as multi-site decentralized automation. And so the use case here is that I have several sites. This could be several labs on one site, or it could be several individual sites separated globally. And we have spoken with a few clients who have this challenge of, we have labs all over the world, and how do we normalize what we're doing and standardize it? And so this allows us to now, in this example, using ELIZA again as an example here, we now are able to run the same hardware in perhaps with slightly different capability sets. You see this one's a little bit smaller. We can run the same hardware with the same workflow in 3 different sites connected by one cloud-based control platform. So we have unified workflows that are shared globally. So when I went into my validation of this, I only had to validate for one instance of this, and now I can push that down to systems locally. And then I can look at where my demand is coming from. So perhaps I've got one site that's underused and one site that's overloaded, and it might make more sense for me to send my client or my internal samples to a different site so I can rebalance that load and make sure that all my facilities are operating efficiently. And of course, all of that data then gets consumed by that orchestration platform and brings it into one location. So it doesn't actually matter where you are in the world. You can always access that data and deliver it to your internal or external customers. So that's multi-site decentralized automation. And this is really a software challenge. This just starts bringing together those individual work cells we talked about into one unifiedly controlled platform using cloud technology. The final type of infrastructure level automation I want to speak to is now multi-work cell shared capabilities. So now we have automation. This is looking at a fairly advanced facility where I've got automation running all the way through my building. But there's overlapping capabilities on those. So you can see here, I've got systems that are multiple systems that are able to carry out tissue culture, and I've got several systems that can run cell-based assays and several systems that can run ELIZA, but perhaps they're all subtly different. So perhaps my cell-based assay system on one floor has the ability to do imaging, whereas the one on another floor is looking at flow cytometry or fluorescence as an endpoint assay. And perhaps my ELIZA systems have different throughput capabilities, and perhaps my cell culture systems have different incubator conditions. So the capabilities vary a little bit from system to system, but generally speaking, they overlap quite a lot. Now, if I want to run a campaign of experiments, I can look at this whole building and all of the automation within it as a set of tools that are available for me to run my entire experimental campaign. And again, this becomes a digital problem. So you would look at something like our software platform to then look at your requirements of your experimental campaign you want to run, the timings of those, the capabilities that are needed for each system, the throughput required, and then look at all of those available resources throughout the building and schedule each of those individual executable runs to happen on the right system at the right time. So it might look at, oh, my ELIZA system up here is not got the right capability set and it's overloaded in terms of its usage. So I'll use the one down here because that can deliver on my capabilities. So I'll schedule that system to run next Thursday. So this becomes quite a complex building-wide infrastructure challenge that can all be handled by one single orchestration platform such as ours. There is also, of course, a data implication for this as well. Now, because all of our systems are connected through one platform, we're able to then harvest data from all of those platforms and consume that into one into the single orchestration platform, and then have that connecting directly with whichever other cloud-based infrastructure, so our digital ecosystem that might exist for our deep analysis or our data storage or archiving or whatever that might be. So we're delivering highly contextualized, deep metadata-rich data sets from the whole experimental campaign into one data lake ready for consumption by other things. So we can see some huge advantages to this kind of automation as well, but I appreciate that this is now a future state that very few labs are really thinking about right now, but it's what we should be thinking about as we head towards the future. And this will give us this ultimate maximum utilization of automated work cells, because now they're running not just on singular demand, but multiple demand around different campaigns, and scheduling the usage of them to maximizing the efficiency across the different demands that they're being placed upon. And of course, we get a unified metadata enriched data set out at the end of it as well, and that data continuity is kept. So of course, I'm from a provider of solutions for this space, and so it would be remiss of me not to speak a little bit about how Automata can actually support this kind of journey to the lab of the future. And so I'll speak a little bit about our hardware and our software first. So Automata primarily builds something called Link, which is the first fully automated lab bench. So we took a core piece of lab infrastructure and said, perhaps that should have an option to have automation running right through it, so that we can utilize the space better and drive more easy adoption of automation into labs that perhaps don't have it right now, and make best use of all of that space that is already there. The Link bench comprises three main areas. We have a robot running along the front of it on a rail. And that robot is really there just to tend devices. And that'll become clear when I show you some videos in a moment what I mean by that. But what we see on a lot of classical automation systems is you put a robot in the middle and immediately becomes the bottleneck to everything that happens on the system. But it's not something that you can then easily solve, because it's very hard to then put another robot in to solve that problem. What we need to do is solve for that bottleneck in a different way. And the way that Automata's approach that is with the transport layer. So the transport layer is easier to explain with a video in a moment, but I think, consider this our labware superhighway. So it runs underneath the top surface of the bench, and is able to carry individual pieces of labware to their point of use, ready for picking up by our robot and delivering to devices just in time. And then, of course, we've got on top of everything the benchtop. There is a status light that runs along the top of this bench, and then on top of that is where we put all of our devices. So it's where our instruments would typically be placed. Just to further explain the transport layer, here's an animation of one of our systems running. And you can just see as it zooms in, labware being moved around on that transport layer from bench to bench, and so it goes to the right place just in time for it to be delivered to the devices on top. To show you that in real life, here's some footage of our transport layer videos from underneath, so you can see some of our cable handling running here. Some of our barcode readers that are embedded under the tables. But you can see one of our pucks transporting a piece of labware from bench to bench, bringing it to the front of the bench just in time for that the lab robot to remove that piece of labware and then go and pick up the next one and service the devices that sits on the bench just above it. Actually, later on, I'll show you a video of this very same system viewed from the front, so you can see how that fits into the bigger picture. The Link bench can be bolted together in a number of different ways. So I've just shown you a couple of linear systems that are shown on the top right here, top left, where we have our transport layer running through the system. And then actually I've just shown for an example here, we don't always utilize the transport layer. Sometimes we take it out and create a bit more vertical integration space. We can also add shelves to go even taller depending on which devices we're using. So we have a lot of vertical space we can utilize here as well for really compact systems that don't require quite as high a throughput sample logistics. We can then bend the system around corners. So we've got benches that provide inside and outside corner configurations. This becomes really useful when we need to wrap things around the edge of an existing lab and utilize that space maybe in a U shape or even going around a pillar. And then we have a configuration that is increasingly popular, which is the back-to-back island system. So now you can see we've got 2 runs of benches, so 8 benches in total that are back-to-back with robots on the outside, and labware can move through the whole of this system with that unified transport layer running underneath, so that labware can go from one side of the system to another. And this system configuration is particularly useful when we want to start putting systems into containment, for example, because it becomes an easier system design. Our software is cloud-based, where so any users can log in from anywhere, depending on their permissions, and do everything from workflow design using drag and drop node-based workflow configuration through to simulating and controlling the execution of those runs, all from a PC or a tablet or a phone. So how does that work to start bringing together this orchestration of infrastructure level automation? So I'll show you a few more in-depth features of our software, because it really does start becoming a software problem once you've got around the system design challenges. So this is what it looks like when you log into our software platform. You can see we have a number of, this is just looking at one work cell with one particular user. And you can see a representation of all of the different runs that are currently going on in parallel on that work cell. So now we're talking about multi-run implementation on a single work cell. We can also look at our work cell runs. So here you can see each line here is an individual execution, if you will. And some of those have been finished. Some of those are currently running. Some of them are queued. And we have this one at the top, which is got this red highlight because it's now ready to run. So you can see it has a schedule button next to it. And so what I can now do is start calendarizing those runs. So this run, when I go into it, I can now click on the schedule button and I can start deciding when I want that to run. And the system will show me when the system has availability to run this particular batch of samples. And I can also change some of the core parameters that I might want to address with this particular work cell. So here, I might need to change my reagent. And actually in this example, this is for a system that utilizes or consumes files that drive some activities on the liquid handler that have been generated by a LIMS system. So we can upload those files because it's not directly connected to the LIMS in this particular case. So now I scheduled that run, that now appears in my run view, where I can see all the runs that are currently executing. So there's several runs running in parallel on this platform, and our new run is scheduled to start after those have finished. So now I have a view where I can start looking at a multi-run. I'm just going to slow this down because it goes very quickly. We can now look at a multi-run environment. So this is a system where actually we're running 3 executions of a 3-batch experiment each. This is a real system in our lab that's running ELISAs. And you can see the system, now we can view that we started the run 1 and then we started running run 2 concurrently. And you can see all of the activities that are happening, and each set of activities is color-coded by individual batch. So batch 1 is being washed, sealed, shaped, peeled, washed, and so on and so forth. But this is all happening in parallel. Of course, everyone wants to know about what happens on the system when something goes wrong. Stuff does go wrong with automation. Anyone that tells you it doesn't is misleading you. What we aim to do is minimize the number of times things go wrong and make sure that when something does go wrong, it's intuitive as to what you should do. So in our system here, run 1 has now, we've gone into an error state. We have to get an error code for the device in many cases. So here we've got an indication of what that error is going to be. And we've got a number of actions that the user could take to resolve that. But we get some strong visual indications that something isn't quite right on the system, as well as, of course, the benches themselves, those light indicators would flash red as well. And now we can move through that and resolve that error. I'm going to speak a little bit about our software architecture before closing up with a couple more specific examples. So this is a fairly complex slide, but I wanted to make sure you're aware that we have different kinds of users would feed into our platform. So we have like 21 CFR Part 11 enabling user control, where people might just be an operator or an administrator with full control, or a workflow designer, who then feed into operating our platform, which runs on AWS. And that platform, once you've created a run, will send data down to a local instance of our software, which is actually embedded in our hardware. So it's actually embedded in the bench, called our hub. And the reason why we run things this way is if this connection were to break mid-run, all of the data required to execute upon that platform is actually stored locally. So network failure is never going to impact on your runtime. and you can interact with this more locally. That hub is also handling an awful lot of the data as well. So that hub is consuming data from instruments, which may be fed in some instance back into the cloud-based platform and through that into through some data piping into your data lake or your ELN or your LIMS. But it might also go directly from your hub into your LIMS system or your ELN or your data lake. So we have a couple of options of how we drive that data continuity into the rest of your digital ecosystem. So last but not least, I want to talk about what would be the real impact of this for my lab. And there's a couple of examples here that are quite different. The first one I want to speak to is actually a very high throughput ligand binding assay that we worked on with a client, where before adopting the automation that we delivered, people were running individual appliance level automation, shall we say, and then handwriting data about what they'd done into a notebook, which all then got uploaded. SOP said immediately, more practically, it was like on a Friday afternoon into the LIMS system. The only bit that was really automated here was data coming from the plate reader could be manually uploaded, but all of the actual process steps were all manual. After implementing our platform, we now, for each of those instruments, are able to log the tasks that have happened and record the data that came along with those. So a lot of this data here is actually system data or process data. So probes measuring temperature and humidity, logging timestamps and other metadata and activity from the individual devices that we're running, such as the incubator performance or when things were sealed or when things were put through the plate washer. And we can combine that with the plate reader data to deliver this metadata rich data set about everything that happened and take away all of that handwritten requirement and deliver that directly into the client's LIMS and Azure-based data lake in this case. So in this instance, we actually delivered a 13 times improvement in the number of data points per sample from the automation, or per plate rather. So they were collecting around about 3 data points per plate before our platform, 39 afterwards. Quite a huge impact in terms of measuring the performance of that experiment. Jumping back to something I shared earlier on, so this is now a completely different example where we think about end-to-end clinical genomics, so something completely different. We've been working on a system that is very similar to the one I shared for NIPT. It's actually a different application. And in that instance, what we're seeing is a 3 times throughput increase over what they were performing with their appliance level automations. This was actually a reasonably automated laboratory. And the knock-on effect for that was the number of staff didn't reduce, the number of staff stayed the same, but the staff cost per test went down dramatically. So we saw this 70% reduction in cost per test. And then we start seeing this enormous decrease in manual interaction. So we're raising the consistency of our experimentation as well. So this is the kind of impact we see when we implement this sort of scale of end-to-end infrastructure level automation. All of that may have been a little bit overwhelming in terms of this huge scale of automation I talked about, but I stand by the fact that we should really be thinking about how we go from where we are now to that. And so if you're at the appliance level automation, perhaps think about what the next steps might be. If you're not automating, think about what the appliances are that you need to get first. Find a core problem, start automating, and then plan to scale. But have a plan and start thinking about. So in this instance, going back to the NIPT example, we went from a standalone liquid handler to fully automated end-to-end workflows. And we didn't do this in 0 to 100. We didn't go from nothing to that final step. We've gone through a phased delivery and really planned out what that change management should be as we move from low to no automation to real lab of the future stuff. And so with that, I will close my talk. I can leave you with a pretty video for a moment of that same system I filmed from below the bench earlier on, just showing you our platform, our robotic arms interacting in parallel with a number of devices, working with our transport layer underneath to really handle those plate logistics. And I'll be happy to take any questions. Thank you very much.
All right, great. Thanks very much, Russell, for a wonderful presentation. So at this point, we are about ready to move into our question and answer session with the audience. Again, for those of you who may have joined us late, you can send in your questions by typing them into the Q&A box on the right-hand side of your screen. Even if you don't have a question, we invite you to leave a comment. Let us know how you enjoyed this presentation, if you found the information useful, and if you'd like Russell and the Automata team to reach out to you following this webinar. I'm also going to put up their website is on the screen in front of you right now if you would like to visit them. And we have some, I'd like to remind you to visit the handouts section on the right-hand side of your screen for some supporting information for this event. And we do have that poll also if you'd like to comment for your chance to win a gift card courtesy of Lab Manager. So Russell, thanks again. Let's jump into the audience questions here. This first one says, this all seems like a huge transition. So where do I begin if I want to highlight some automation targets in my lab?
Yeah, that's a really good question. I think we often talk about this, like, where do I start when we talk about adoption of automation? I always encourage people to think about try and get to a point very early on where you're setting a goal. So when we work with clients on this, and we do have clients that come to us without a specific goal at the very beginning, we'll work with them to sort of really come and do and look at their laboratory and the process they're running right now and try and identify where their current bottlenecks might be, where their current maybe data continuity problems might be, or reproducibility challenges might be, but try and land on a goal, which could be one of those things. It could be increased throughput. It could be, I don't know, reduce manual interaction at this point. It could be generate more data here. It could be add in another analyzer, but you need to figure out which of those first goals is most tangible. I think to try and leap to some of the automation examples I've shown today is possible, but it's a big leap. We do work with clients that are doing exactly that, and we build a really strong change management program. But the success of implementation of automation and the adoption of it by people in your lab is better served if you start off with something tangible and meaningful to them and then scale with it. So set a goal and think about what's small and go from there.
Okay, great, thanks. Let's go on to the next one. It says, can your software be run not in the cloud?
Yeah, we get asked this quite a lot. The simple answer is no. I mean, we are looking to provide a state-of-the-art solution that will take you into the future. We know that there are some sites that have challenges adopting cloud-based infrastructure, but actually we've not really found a site where it's been, not real many sites where it's been an absolute blocker, and we'll work with you to get past any of the challenges there. But no, our software is designed to be run in the cloud, and you reap all of the benefits that come with that. So I know it's probably a long answer now, but we can use cloud computing technology to deal with some really knotty scheduling problems, such as how do I deal with time constraints through the system. And of course, we can then do like practical things like allow you to monitor your system from, I don't know, your morning cup of coffee, wherever that may be. And all of these things are enabled by cloud infrastructure. So when we advocate for all of those things being really positive.
Okay, great, thank you. We have some more questions coming in from the audience. If you scroll to the bottom a little bit, this next one says, I know it will vary a lot, but what is the cost range for a link?
Yeah, it does vary a lot. I think I'll be very honest, I'm not going to answer that super directly because it varies too much by project. We have projects that are in 6 figures and projects that are in 7 figures and greater, right? So it really depends on what you're trying to do. Also, the other bit that can really impact the cost of these is the devices that go onto them, which is a little bit out of our control, and whether you need to add on things like containment. So yeah, sorry, that's an indirect answer to that, but I think we're best served getting to an estimate for a project fairly early on in the process of looking at what workflow you want to automate, looking at the space you have, trying to figure that out, and then figuring out what a cost estimate might be. Yeah.
Okay, thanks. This next question says, how does the bench communicate with the instrument? Is this something I could set up myself, or would it require external support?
Yeah, really good question. So we at Automata are an integrator of devices. So all of those third-party devices, we provide the integration for that. We factory acceptance test that in many cases and then deliver that to your site. So we take full responsibility for the connectivity of the Link platform to the devices that are going on it. So it's not something you should have to worry about. So all of that communication is handled by ourselves. Of course, the other example where external support might be required is if we have to work with the third-party vendor. And I mean, that is true in some specific examples where we need some extra support and subcontract to that device vendor to bring some extra communication support. But most of the devices that are out there that are automation friendly have really well documented APIs. We develop the plugins that then both physically control that and deal with any data challenges that go with that. And then, of course, we also even go beyond that and start delivering data connectivity to your LIMS or ELN or data lake or whatever that might be. Yeah, next question, please.
Sure, thanks. Let's go to the top of the list. I think we have time for a couple more. If I use existing instruments, can I still get access to them on the automated platform? Some of them are really expensive.
Yeah, it's an interesting one. So if you look, I've been asked this on every automation company I've sort of had the pleasure of working with, and it varies how you deal with it. One of the beautiful things about the Link platform is that because we've put the robots on the outside and we've inverted that design, now all of those devices, or almost all those devices, now face outwards on the system. And so most of those devices, not all of them, can now be accessed even when the system is running, but can be accessed manually. And I think the real clincher tends to come in on some of these really expensive ones. I've had a few projects where we've worked with things like imaging systems and high content images where they could be $1 million in their own right, and their runtime's quite long. So we tend to locate those on a position of the system where they're more easily accessible. And as long as the automation system isn't using it at that moment in time, we can flag to the user when it's available and they can walk up and interact with it manually. And of course, all the robots themselves are these are all collaborative robots, right? So it's perfectly safe to walk up while the whole system is running and interact with those devices. Hopefully that answered that question.
Okay, perfect. Thank you so much. We have time for one last question. How did the client work out what their targets could be for automation in the genomics case study?
Oh, yeah, that's an interesting one. So I think I alluded to this, that this wasn't we didn't go from nothing to everything in one step. And we did pick on some individual areas to start building upon. And this maybe I answered this a little bit in the earlier question where we sat down with the client and we did an awful lot of walking through their existing workflows and also what devices they had available in their own lab already. And what surfaced was some particular areas of problems. So in their case, it was mainly around the extractions. So we started focusing on the extractions mainly because it was really onerous to do it manually and it was the bottleneck to anything else working. So we thought if we can solve that problem, then we can start thinking about what the other areas we might automate as coming afterwards. And actually by doing that, we defined a work cell right in the middle of the process that helped us to define the work cells that went upstream and downstream of that. And then it became a lot clearer on how we might transition to a larger end-to-end system in the future as well. Yeah.
Okay, wonderful. Thanks so much.